So this is a brief summary of my talk. And recently I have started beginning always with this same preamble. This is a very interesting, I don't see that the flipping is working.
It's working now.
Sorry? Aha,
it looks
okay,
fine.
Fine. Yes. So anyway, this is a really instructive historical tale with direct relevance to the high-TC superconductors. And this is that there is this famous Hund's rule for freestanding atoms. It has no exception in nature. That when you have an open orbital, the electrons will arrange themselves in a high-spin state. Okay? And this was understood by Slater in the 1930s. This was understood by Slater in the 1930s to be due to the intra-orbital repulsion. So he said in a d orbital is small and you have two electrons inside and they like to go into different orbitals because then they minimize the repulsion. And this was the state of affairs until the late 1960s when the quantum chemists, not physicists, realized that this was completely wrong. This is an incorrect explanation of this rule. The correct explanation is the following, that
That's the next room.
there's the next room. Okay, yeah, what can we do? The correct explanation is the following. When the electrons are in a high spin state, that means they're spin symmetric. That means that the spatial part of the wave function must be antisymmetric. The antisymmetric wave function has the smallest possible screening of the ionic core, which means that in an antisymmetric configuration, every single electron sees the ionic core and the atom contracts. There is a huge energy gain from the ion-electron attraction. And this is what drives the effect. It is 10 times bigger. This central Coulomb effect is 10 times bigger than Slater's explanation, okay? Which accidentally gives the same sign, okay? So everybody was, so to say, misled into believing that this was the reason. And in fact, there are a few recent papers. You see 2005, 2008, that's quite recent for something which started in the 1930s, where they showed, for instance, that with helium you can get the excited state correct with only S-wave mean field. In other words, no angular correlations at all. This is purely central field effect. And this has a direct repercussion for the high-TC superconductors, because in the pnictides, the iron T2G orbitals are caged in the tetrahedra, which are set up by the E2G orbitals, and this means that they behave like in an atom of fixed size. So the Slater's generally incorrect explanation of strong correlations is correct for the pnictides, because the size of the orbital is fixed by a stronger scale, by the binding scale. While in the cuprates, you have the bridging oxygen. The bridging oxygen allows charge transfer from a correlated atom to an uncorrelated atom, which fixes the size of the lattice, and this is effectively the size of the atom in the lattice, okay? So you have essentially the modern explanation of Hund's rule is active there. And sorry, I'm, what has...
You go backward, I mean, it's inverted.
Oh. Okay, I'm sorry. Okay, so now I go this way. Okay, very good. Now, and here is the proof, if you like, that central fields and Coulomb fields are sufficient to explain the most outstanding spectroscopic feature in the cuprates, and these are the Fermi arcs. Actually, if you do a DFT plus U calculation, no DMFT or strong correlations, whatever, You just treat the dopant ions as real physical ions with real Coulomb fields, which this calculation can do. You will find in a zero temperature, one body calculation, you will find arcs which grow just as observed with the doping. Okay? And this is a little bit more detailed picture of the same thing. You see here, this number 1 cut is this one, the diagonal cut, and the number 7 is at the antinodal point, and you notice between 4 and 5 we start getting gapped. And this is how it looks in the calculation. You see, this is a perfect dispersion going through the Fermi energy, and then you have a preformed gap going down, and somewhere between 4 and 5 it bites the Fermi surface, and here you have the pseudogap. So essentially what this shows is that you have a normal Fermi liquid in the arcs, and the only reason you have the arcs visible is that actually the zone which includes the dopants is much smaller because it corresponds to a much larger unit cell. And when the unit cell including the dopants is bigger, okay? And so when this unit cell including the dopants is unfolded into the standard cell, then this unfolding gives you the arcs. In other words, the arcs are a simple kinematic effect. They're essentially a projection effect. There is nothing, the arc fermions do not have to be anything but an ordinary Fermi liquid to get an arc in this approach. But the next question is, what is going on in the underdoped planes? This is the P regime of Neven. Now, what has to be understood is that this is an idea which was first published in 1989, and we have managed actually to prove it by some direct experimental observation. This is, you see here, maybe I should have said it before, you see here, you can see by this integrated charge around the strontium dopant in LASCO, you can see very clearly that the charge stays localized in the vicinity of the ion. In other words, the doping of the planes is actually some kind of Coulomb domino effect propagating through the insulating layers, by which finally the copper exports a whole or part of a whole onto the oxygen. And this partial export of the whole from the copper to the oxygen can be beautifully observed by 017 NMR splitting. It is this Damian Rybicki 2016 Nature Communication paper. Here you see the green is you see this is a hole on the copper. The green is the electron on the copper. So you can see, and this red is the electron on the oxygen. And you can clearly see how you go from the low TC, high TCs like LASCO to the high TCs, how this transfer happens. Essentially, all of the material dependence in the cuprates is in this localized hole, which is shared between the coppers and the oxygens. And then this is my, so to say, image of this Coulomb lever, which starts with the dopant and then finally pushes the hole onto the oxygen. And the consequence is that you have a localized hole as an ionic molecule or a small polaron, and now exactly P, the remainder of the charges are hopping. This is the figure which you already saw in Neven's talk, and you can see that there is a broad transition from P to 1 plus P. This is theoretically a very important point, because these broad transitions happen in the average quantities when you have a first order phase transition microscopically. Because a first order phase transition has this microscopic characteristic that at a given site it always is either 0 or 1. It is always discontinuous at a site, but because not all sites flip at the same time, you have a sort of smoothed out transition macroscopically. Okay? This is very different from a second order phase transition, which has a macroscopic discontinuity in this sense. It would have a discontinuity in the occupation number visible on the average. Okay, so oh, sorry again. Yeah, And now the question, how do they hop? Okay, so now we have some p charges on the oxygen. How do they hop? And now here enters the main player actually. This main player was first noticed in a very famous paper by Eva Pavarini of the Stuttgart group, Physical Review Letters in 2001. They realized that the 4s orbital of the copper is actually the main hopping channel from oxygen to oxygen. And this is because the copper d orbital is blocked. It is blocked precisely by these strong correlations which we have been talking about. So the electron on the hole on the oxygen takes the easy way around. This overlap between the 4s orbital on the copper and the oxygen orbital is something like 2 electron volts. It is the biggest overlap in the game. And despite the fact that the s orbital is far away energetically, you have a second order process which goes like t square over delta. And t is, say, as I said, 2, so square is 4. And delta, if delta is 6, that's already 2/3. Okay, so that's a very big effective hopping, which is much bigger than the direct chemical TPP, which is only 0.1 electron volt. And this observation is enough to understand why you need, when you fit ARPES in a 3-band model, then you always need to put an artificially large TPP, because this conflates with the 4s process, okay? So we have a fast virtual process which completely avoids this correlated mess in the d orbital, okay? And now there is a very interesting symmetry of this model, highly significant for the cuprates. It's almost like a conspiracy. And it is this, that when you sit on the diagonal on the zone, so kx is equal to ky, then the wave function is orthogonal to the 4s orbital in wave function space, in Hilbert space. Essentially, the secular polynomial factorizes for these particular values of k on the diagonal. And the effect is that the diagonal carrier does not see the 4s orbital. Net effect is that it only has the TPP hopping to use. And look at this. This is one figure which has been repeated many times. You have the same slope of the diagonal electron independent of doping. And the reason is that they have like a mouse hole to go around everything, which is small. And now when you go to a higher energy scale, then you start bumping into the d orbital. You cannot use the s orbital here because you don't see it in wave function space. It's the wave function is orthogonal to the s orbital. Okay? So essentially, what we believe, this is a narrative. This is not something which could in principle be proven by calculation, but this calculation has not been done. We have here this fact that this here is discontinuous, and this gets more and more continuous as you go to higher and higher dopings. This actually corresponds, we believe, to the transition from the copper-oxygen bond from ionic to covalent, the DP bond, okay? In the underdoped regime, the DP bond is ionic, and you have a localized hole. This is the CuO4 ion molecule. And on the overdoped side, it becomes covalent, which means you have a Fermi liquid, but this Fermi liquid does not superconduct because, as Neven has pointed out, this localized hole is important for the glue. Okay, so you have a lot of Fermi liquid spectral strength coming in, but the superconducting strength is coming down. Okay, and here, again from this old calculation, you can see the difference between the ionic bonding and the covalent bonding. In the ionic bonding, you can see that the copper has pushed, red is positive charge. Here the copper has pushed positive charge onto the oxygen, and this, but at the price of having negative charge here. So you have a Coulomb gradient here, which prevents the hole on the oxygen from hopping back onto the copper. Okay, that's the nature of the ionic bond. And here you have a covalent situation like any three-band model without any correlations, where you just lift the Fermi energy, and then you can see that both the copper and the oxygen orbitals have acquired positive charge. In other words, they are filling coherently. Okay, this is characteristic of the covalent bond. Okay, so what we have here is that we transition from an ionic bond here to a covalent bond here, and this is the reason why the Fermi liquid density increases, but the superconducting density decreases. So finally, the next subject, I don't know, I'm well on time, right?
Yep.
I have another 15 minutes, yeah, that's good.
Well, yes.
Yeah. Okay. I will not use all of these 15 minutes, I promise. I'll leave some for the discussion. Yeah.
Well,
okay.
if you're a good boy, we'll
Yeah.
get you champagne.
Anyway, my next subject is the question of dimensionality and how we can look at the dimensionality of the superconducting state in the cuprates from this point of view. Now, there are two things to say. One is general and one is special. The general thing is that recently, much to my surprise, we have discovered that the Hohenberg-Mermin-Wagner theorem, the famous theorem which everybody cites for the past 50 years to say that two-dimensional superconductivity cannot be, this theorem is completely ineffective. It is mathematically exact, there is no mistake in the theorem, but the theorem says that infrared fluctuations of the density, electronic density, will destroy the superconducting order parameter. And the simple question is how big the sample must be for this to happen, because the infrared fluctuations in a real sample are cut off by the size of the sample. And when you do the calculation, ta-da, this is, you see, the logarithmic suppression is very weak. That is the whole point. So when you turn the equation around, it turns out that the size of the sample must be smaller than x of Fermi temperature over Tc. Fermi temperature 10,000 Kelvin, Tc 100 Kelvin. This is x of 100 in angstrom, okay? You turn it to meters and you get 10 to the 30 something meters, about 1 million times larger than the visible universe, okay? So to suppress Tc of 100 Kelvin by the Hohenberg-Mermin-Wagner theorem, the sample needs to be 1 million times bigger than the visible universe.
So you change the universe, right?
Yeah, okay. So whether that has something to do with quantum gravity, I leave it to you, you know, to decide. Anyway.
So we all agree, right?
The point here is that, so that's absolutely no obstacle at all.
Right.
That's the general thing. But the special thing is, there is a wonderful little experiment very early on, which shows that actually this is a torque experiment, like which shows that the material is becoming more two-dimensional as you go down in temperature. Okay, so the high Tc's are more three-dimensional around Tc than at 10 Kelvin. Okay, and so there is an intrinsic two-dimensionality. This is already was established in 1990, and I would just like to I would just like to make a comment here that many times people say that somehow BCS is not correct, or that the problem here is that nobody has followed the BCS arguments seriously outside of Gorkov regime. Okay, Gorkov derived, as we all know, the Landau functional from the BCS theory. But he only did it for a physical regime with such as for lead or mercury, okay? And these materials are in a completely different regime. In particular, the pair is probably very, very small. This picture which we have been developing means that the pair is practically of the size of a unit cell. And to my knowledge, nobody has tried to rederive, follow Gorkov's derivation in this regime, where the size of the pair is much smaller than the distance between the pairs. Okay? So before anybody says that BCS does not work, I would like to see such a calculation. Okay? There is another thing, and this is that the self-consistent equations of state normally determine the size of the pair. But here, the size of the pair is cut off by the size of the unit cell. This was pointed out already by Friedel in the 90s. He noticed that a high second critical field of 100 Tesla means that the pair is so small that it is no longer determined by the self-consistent equations of BCS, but rather it is a given number for those equations. Again, completely different regime. So, as I said, the pairs must be very small. The pairing involves the Cu4s orbital. So, in other words, the order parameter must be 0 on the zone diagonal by symmetry. The fermions on the zone diagonal cannot participate in superconductivity because they do not see the channel through which they scatter. Okay? There is a natively two-dimensional, and now one beautiful side effect of this whole story is that tunneling, if the pair is very small, then the tunneling between the planes of this pair is point-like, which means isotropic, which means that the order parameter should have a small S admixture coming from this isotropic tunneling. And lo and behold, Miller, Alex Miller in 97 and Hugo Keller, they actually nailed it. You see, they have this is an NMR, I believe, probe. So bulk 3D probe sees a little admixture. You see, this is a D wave line, this is an S wave line, and even at that time, Alex Miller pointed out that pure D wave superconductivity in cuprates is found only by surface probes. If you have a bulk probe, then you will have a small S admixture. And this fits perfectly into this picture of very small pairs tunneling point-like between the planes. Okay? And finally, the mechanism then involves this local hole, but we do not know yet what internal excitation of the Cu ion is involved. And again, there is a 94 paper by Little and his group, and they repeated this in this conference in 2007, where they identified two excitons which are good candidates for the localized calculation with the glue. And interestingly enough, this experiment was also noticed by Miller, who said that could probably be the glue. Okay, so there is a picture of a localized glue for these holes which propagate via the 4s orbital. Okay. So finally, I come to my conclusions, luckily with 5 minutes left for the discussion. Conclusion. The arcs are a kinematic effect unfolded from a smaller zone. They're a simple projection symmetry effect, nothing to do by themselves with any intra-orbital correlation. It's a one-body kinematics. Okay. Now, sorry. Second, these partial charge transfers, which are created by doping, they kind of induce a sharing of this localized hole between the copper and the oxygen, and this sharing is the last of the material dependence. Beyond that, when you are already on the oxygen, the cuprates are universal, because the chemistry involved in the oxygen metal, which is so created, is determined by very few overlaps, which are the same in all cuprates, because the lattice constant is the same in all cuprates, okay? Roughly speaking. So the main conduction channel is a high energy virtual process, which is completely uncoupled from the low energy garbage, so to say. The delta PS, which is involved in this, is at least 6 electron volt. Okay, so what we have is an anti-adiabatic, effectively, Fermi liquid, whose one-body properties are determined by the highest scales in the material. These highest scales are the Coulomb scales, which are responsible for the material binding. There is no talking back to those guys, you know. It is like an elephant. So the usual feedback into the effective mass, which happens in the standard Landau-Fermi liquid theory, it is absent here, simply because a stronger player says what the number is, and end of story. The usual adiabatic argument functions if the dominant propagation mode is low energy. Then it gets entangled with the lattice and with all sorts of other things. But here the dominant propagation process is 6 electron volt virtual process. Okay? And so, as I said, at overdoping, the 3D 2p bond becomes covalent, which increases the Fermi liquid weight but destroys the superconductivity because the localized hole is important for the superconductivity. And so finally, as I said, superconductivity in 2D is all you need to look at because the samples are smaller than the visible universe. Okay? So I thank you for your attention.
Question here?
Yeah.
So regarding the first
Don't need microphones.
Regarding the first statement about the arcs being a kinematic effect, so you say that based on simply on a supercell effect on a DFT calculation?
Yes, actually this was done for the first time, and this code we used was developed for disordered alloys. Because in alloys you have the same sort of thing, where you can have the original parent material and it has these peaks, Fermi liquid peaks, surface, whatever. And then you start alloying it, and when you alloy it, then very quickly translational invariance is lost. So the theoretician would say that there is no zone. But in fact what you observe is that there is a zone, and all that happens is that the peaks are no longer resolution limited. Okay? And so there is a very gradual evolution, destruction, so to say, of the zone. And this code was developed in such a way that they take a large zone, and a large unit cell, and then they systematically project the small zone out, they unfold it. It's called an unfolding algorithm. It's actually undergraduate textbook, if you like, algorithm, but the problem is if you have 100 atoms per unit cell, then a supercomputer will do it for maybe 2 days. Okay, so
but it's not just a simple periodic supercell.
No. In our calculation, it was because averaging over disorder was a bit too much for us at the time. But I know what the effect of disorder would be. It would just broaden the peaks a little, because that was done in the alloying calculation. Okay.
We have to be because we are online. Quick one. Quick, please.
Just concerning this supercell calculation.
Yeah.
So the bands can't just simply stop. So is this arc bending backwards again, or is it a pocket?
No. You have a small zone, and in this small zone you have several Fermi surfaces which all properly close upon themselves. Okay, and then you project this, you unfold this small zone into a large zone, and each point which crosses the Fermi energy maps onto some point over there. But of course, like a superposition. It's not one-to-one point.
But the band from the arc goes then back again into the arc. It's
I'll show you. You can see it on the. Sorry, I am. You can see it on the figure a little bit. It actually goes from one regime to the other. You see here, it doesn't. Here you have still a gap, but there is no bending back. And then as you go towards the very antinodal point, you start getting some bending back. Okay, that is what happens.
Right. Okay.
Yeah.
We have to cut it off. Thank you very much, Denis, because we have more speakers.
Okay.
This is for you. The next speaker is
Ivan Macho Aprile from Geneva, and he has some staggering new results with STM, and basically reveals that one McDonald vortex core states